Good morning. Today, I'd like to talk a little bit more about the effect of acceleration on an individual as related to the members of an inertial reference frame. In the previous video, we considered the situation of an individual who starts off at the origin of an inertial frame and then experiences uniform proper acceleration. That is, in each momentarily co-moving reference frame, the individual experiences a constant acceleration, which I'm calling A. We figured out by using Lorentz transformations and the definitions of various quantities a wide variety of facts. We first figured out that the speed v dx dt is actually equal to the hyperbolic tangent of a times tau, tau being the proper time. Direct calculation shows that the gamma quantities, which appear in the Lorentz transformations between O and each momentarily co-moving reference frame, can be expressed as the hyperbolic cosine of the acceleration times the proper time. The relationship between coordinate time t and proper time tau is that acceleration times t is the hyperbolic sine of acceleration times proper time. The x-coordinate of Fred is 1 over a hyperbolic cosine a times proper time plus a constant of integration. I'm leaving that constant in for now because this will allow me to think about individuals that start off at places other than x equal y equal z equal 0. If you do start at the origin, though, beta needs to be negative 1 over a. Combining the previous facts, I found out that v, which is equal to the derivative of x with respect to t, is a times t divided by 1 plus a squared t squared. It's not difficult to integrate that last equation and find out that x must be 1 over a radical 1 plus a squared t squared plus a constant of integration that I'm calling delta. I'm leaving the delta in for the same reason that I left the beta in. If we wanted to start at x equals 0 when t equals 0, delta would need to be the negative of 1 over a. For purposes of reference, I'm going to number these equations 1 through 6, and in what follows, I'll feel free to use them as needed. Lastly, we figured out equation number 7. If, according to the O network, Fred has 4 velocity u sub Fred and encounters a photon with 4 momentum p, then I can calculate the energy of the photon as measured by Fred by doing the dot product of the 4 velocity with the 4 momentum and putting a negative sign in front. Based on the preceding formulas, it's direct to show that the components of the 4 velocity of Fred, which I'm just going to call u, according to O, are hyperbolic cosine of a times tau, hyperbolic sine of a times tau, and because there is no motion in the y or z direction, the last two components are 0. For our first situation, let's imagine that Fred is traveling along, and somewhere out in front of him, a photon is emitted along the x-axis traveling towards the origin. As measured by O, we'll say the frequency of that photon is f. I want to figure out what Fred is going to observe. We already know what Fred's forward velocity is as measured by O. As measured by O, component number 0 of the forward momentum is the energy. There is no energy or momentum being transferred in the y or z direction. The amount of momentum in the x direction is h times f divided by the speed of light. And since it's traveling in the negative x direction, we should associate that with negative h times f for the x component of the forward momentum of the photon. When I do the dot product, -1 is eta 0, 0. There's component 0 of the forward momentum, component 0 of the forward velocity, plus eta 1, 1. There is the 1 component of the forward momentum and the 1 component of the forward velocity. Notice there's a factor of h times f in both pieces. Also, there's a minus sign in both pieces. Remembering what hyperbolic sine and cosine are, I can combine that last term inside the parentheses and find out that the energy as measured by Fred is the energy as measured by O multiplied by e raised to the a times tau power. As measured by Fred, as time goes on, if he encounters these same photons as observed by O, the amount of energy that Fred is going to receive from each one of these photons is literally going to grow exponentially with respect to the time that Fred's clock says it is. Very quickly, he's going to encounter radiation that is so blue shifted that it will be probably damaging to him and his measuring equipment. On the other hand, imagine it as Fred is traveling along. From some point behind him, a photon with frequency f as measured by O is received by Fred from the other side. The two vectors are still the same, except this time the forward momentum in the x slot, this slot, is not negative h times frequency, it is positive h times frequency, where by force of habit I've written Greek letter nu for the frequency, so let me fix that. Doing the same sort of Minkowski dot product, I find out that the energy as measured by Fred will be h times the frequency measured by O multiplied by hyperbolic cosine minus hyperbolic sine of a times tau. If we remember the definitions of those, we can write this as an exponential. As Fred's proper time increases, the energy of the photons, which according to O all have the same frequency f, will appear to have a frequency that is reduced by a factor of e to the minus a tau. According to Fred's watch, the energy of these photons, and therefore their frequencies, are going to decay exponentially, rapidly becoming so low that Fred likely will be unable to detect them after a while. So far, our calculations seem reasonable enough. Fred is rushing towards a source of radiation in one case, so he sees it blue shifted, and receding from a source in the other, so he sees it red shifted. What if, as Fred travels along, as measured by O, he encounters a photon that has come in along a path parallel to the y-axis? Fred's forward velocity is still given by this formula. The forward momentum of the photon, though, will be different. The energy is still h times f, but there is no motion in the x direction, so this component is 0. The momentum in the y direction is negative hf because y is decreasing, and the z motion is 0. Eta 0, 0 is negative 1, so I will have inside the brackets negative 1 times the hyperbolic cosine times h times f. Eta 1, 1 is 1, so I'll have 1 times the hyperbolic sine times 0. Eta 2, 2 is 1, so I'll have 1 times 0 times negative hf. And eta 3, 3 is 1, so I'll have 1 times that times that. And notice only the very first term inside the bracket contributes anything. The negative signs cancel out. So the energy as measured by Fred is the energy as measured by O multiplied by hyperbolic cosine of A times tau. If you keep in mind the definition of the hyperbolic cosine, this is certainly bigger than 1/2 energy is measured by O times e raised to the A times tau power. As Fred proceeds along his path, if he is struck by any radiation which, according to O, hits him at a right angle to his direction, then the energy of such photons is going to grow exponentially as proper time increases. Fred will see a blue shift even though the light ray is at right angles to his path. Unlike what happened with the source of radiation ahead or behind, it's a direct calculation, only this component changes sign to figure out that even if the light ray is coming in at right angles from below, you're still going to get this result from the calculation. Radiation that reaches Fred at a right angle according to O is going to be blue shifted. As you go further and further down the path, as proper time increases, the blue shift is going to grow exponentially. I have a thought in my mind, but I don't want to pursue it too much at the moment. Let this thought stew around in the back of your head. Somewhere out in space, a photon is emitted, but for one reason or another, it gets severely redshifted. If it's measured by O, it's infrared or something. But on the other hand, in view of the discussion we just had, if we can rig it so that one of those photons hits Fred at a right angle according to O, then that photon will be blue shifted. How blue shifted will it be? As much as we want it to be. It's possible for Fred to observe the photon that got severely redshifted as not being redshifted at all. You could even imagine this to have something to do with clocks. I'm going to stop talking about that right now, but we'll come back. There are another couple of situations involving our accelerating friend Fred that I want to look at, but I want to make these next couple of videos rather short, so I'm going to stop there for now. I hope that everybody has a good day, and I'll talk to you again soon.